Okay, sorry, I had forgotten to unmute myself. So, dear students, let us start the class. I am showing you a PowerPoint slide, and here I have shown you the 3 textbooks which we are going to use for our syllabus. The textbook which is in the middle is the main textbook, Electronic Devices and Circuit Theory by Robert Boylestad and Louis Nashelski. In this particular textbook, there are a lot of analytical exercises. That is why we have chosen it as a main textbook. But as far as the theory is concerned, can't see the screen. Is the slide not visible? No. Yeah, others can see. Only Nirmit is telling that it is not visible. Maybe you refresh again, Nirmit. For others, it is visible. Okay, let me go on. The first textbook which I have listed here, Electronic Principles by Albert Malvin and David Bates. This is a very good textbook which contains lot of basics of electronics. This book you can keep on referring for the lifetime. And I have uploaded the PDF of this textbook into the Google class as well. Anyhow, in my notes, I am going to share all the PDF as well as the PPT with all of you, and all the common topics which are common to both the textbooks, which I am going to discuss in future. It is always a good habit that don't refer only to the notes, don't refer only to the PowerPoint, keep reading the textbooks also. Now, the last textbook which I have mentioned here, Electronic Devices and Circuits by Millman and Halkias. Its earlier edition was a textbook for me when I was studying BE also, way back in 1983-84. And this book is available even now. Only some portions of that particular book we have included in the syllabus. Nirmit keeps asking me different types of questions. I have been telling you that I have put the PDF in the Google class. Please check in the Google class where I have uploaded the PDF of the first 2 textbooks. If you want to have a hard copy, buy it from a bookshop. Study the subject well. Don't keep on asking such questions for which the answers are obvious. Okay. Otherwise, the time will go on in answering all these questions only. Ask me subject related questions. Don't ask me all other types of questions. The PDF for the 3rd textbook is not actually necessary for you because we are selecting only a few topics from them. That is why I have not uploaded. But if required, I will upload it in the Google class. Okay, and these are the sections which we have chosen for the syllabus, which in detail I am showing it here. And we are going to teach only those sections which we have chosen for syllabus. So, right now I am discussing the sections 4.1 till 4.5 in Robert Boylestad. For the first module and second module, Boylestad is the main textbook. Even for other modules also, Boylestad remains the main textbook. This 8.9 and 8.11 which is there in the 3rd textbook, I have already put it in the notes. So, I thought it is not necessary to share the textbook. Anyhow, I am going to share the textbook in the Google class. Let me go to the next slide. Analog electronic circuits. The code is 19EC34 and module 1. The name of this module is BJT biasing and AC analysis. If you want to see the syllabus, you can always download the syllabus from the college website. In the Department of Electronics and Communication tab, you will find the course contents or you will find the program contents. You can download the complete PDF. So in today's class, I am purposely showing you some slides because we will work out some exercises now based on whatever is discussed till now as the theory part. So let me go to the next slide. We initially discussed the base bias. It is also called as fixed bias. And you are seeing a circuit here where RB is 240 kilo ohms and RC is 2.2 kilo ohms. Now your job is quickly give me the answer by determining the Q point and also find out IC saturation and also find out VBC. Just to recall the basics, you can easily find out IB by VCC minus VBE divided by RB. If you apply KVL at the input side, you will see that there is RB and there is VBE. So it is 12 minus 0.7 divided by 240 kilo ohms. That is IB. Now beta is given. So IB into beta is IC. Now once you find out IC into RC you can find out. So apply KVL at the output side. 12 volts minus ICRC is going to be VCE. So you quickly give me the answer for the coordinates of the Q point. Find out IB, then find out IC, then find out VCE within the next 2 minutes. I'll keep watching the chat box. Okay, it should not take this much time. Sayan has given the answer as IB as 47 microampere and Geetanjali has given the answer 4.75 microampere. VBC is 5.89 volts. Okay, VBC, that VBC let us see later. First I want to know the Q point. Anyway, let me show you the answer. IB is 12 minus 0.7 divided by 240 kilo ohms. See, here it is 12 volts, here it is 0.7 volts with respect to ground. So across RB it is 12 minus 0.7, RB value is 244 kilo ohms. So the answer is 47.08 microampere. Science answer is correct. Now ICQ, or the quiescent collector current, is beta into IB, that is 50 into 47.08 micro, that is 2.35 milliamperes. And if you find out ICQ, you can easily find out VCEQ. VCE quiescent is total voltage at the output side is 12 volts. Remaining voltage is across this RC, that is IC into RC, 2.35 into 2.2K. That milli and kilo, I am not putting it here because it is getting cancelled. So 12 minus 2.35 into 2.2. So the quiescent VCE is 6.83 volts. So what does it mean? The supply voltage is 12 volts. Ideally, we should have VCE as 6 volts. It is somewhere nearer to 6 volts only. So that way, we can say that this transistor is in the middle of the active region. Now, how to find out IC sat? IC sat means we should assume that the transistor is completely switched on, or it is in under saturation region. That means VC is 0 at that time. So we can simply find out IC sat as 12 divided by 2.2K. That is IC sat. This is required for plotting the load line. Now you can see IC sat is 12 by 2.2K equals 5.45 milliampere. Whereas we have got the quiescent collector current is 2.35 milliampere. So somewhere at the middle of the active region only we are there. Typically, VCEQ must be half of VCC and ICQ must be half of IC sat. So you can see approximately 2.35 is half of 5.45 milliampere. So we can safely say that this particular circuit is in the middle of the active region. Now finally we have to find out VBC. VBC is VB minus VC. Here VBC means that base to collector. Whenever we say VCE, collector to emitter, but anyhow here emitter is grounded. So we can simply say as VC as well, but we don't say VC because sometimes this C can mean capacitor also. That's why we generally write VCE. Now what does the VBC mean? VBC means that voltage between base to collector. So what we have to do, base to ground is how much, collector to ground is how much. Base to ground is 0.7 volts. See, VBE junction, this is a base to emitter junction. Emitter is grounded, so base is at 0.7 volts. And collector is at 6.83 volts, which you have already seen. So VBC is 0.7 minus 6.83 is minus 6.13 volts. Now what does it mean? When we get VBC as negative, what does it mean? Recall the earlier discussion where for cutoff region and for active region and for saturation region, we had some conditions. Cutoff region means base to emitter junction as well as base to collector junction is reverse biased. Active region means base to emitter junction should be forward biased, base to collector junction must be reverse biased. Saturation region means base to emitter junction as well as base to collector junctions are forward biased. Now here you can see base to collector junction is minus 6.13 volts, which means that base to collector junction is reverse biased, and base to emitter junction is 0.7 volts, which means it is forward biased. So conclusion is here VBE is positive and VBC is negative, which indicates that base to emitter junction is forward biased and base to collector junction is reverse biased. This means that the transistor is operating in the active region. It is also called as linear region. Okay, this is the answer. But VBC can also be VCC minus ICRC minus IBRB. How is it so? VBC can be VCC minus ICRC. No, VCC minus ICRC at the output side. IBRB is at the input side. There are two distinct loops here. Don't get confused with the too many circuitry here. I will show you. There are two distinct loops here. See, one is this loop. This is the input side loop. From supply voltage through RB, current is coming to the base and going to ground. This is one loop. And this is the other loop. This loop is at the output side. So it is VCC is applied here, ICRC and VCE is here. So output to input, the relationship is only the beta, nothing else. Don't get confused. The transistor is going to take the base current and then it is going to switch on, and the switch, when it is the switched on condition, the collector current is dependent on the base current in terms of the factor beta, and that beta is given by the manufacturer. So that way don't mix up the equations. Okay, IBRB cannot be mixed with VCC minus ICRC. VCC minus ICRC is at the output side, whereas IBRB is at the input side. Don't mix them. Okay, I hope this point is clear. Let me go to the next slide where I have next exercise. This base bias is also called as fixed bias. We had one exercise. Let us see the next exercise. This exercise, quickly you have to give me the answer. Students have to be active. You should have calculator always adjacent to you whenever there are these classes, because in the second year of electronics and communication, all the courses will have lot of calculations or lot of mathematical approach. You should always have a calculator with you. Okay, now look at this particular exercise. Given that VCC equals 12 volts, ICQ is 2 milliampere, VCEQ is 6 volts, design a fixed bias circuit with beta equals 80. See here, Q point is given. Q point is given, supply voltage is given. You will have to visualize the circuit now. Now design the fixed bias circuit means you have to find out the value of RB and RC given beta equals 80 and determine whether BC junction is reverse biased, base to collector junction is reverse biased. Now quickly work this out and tell me the answer. At the input side, it is 12 minus 0.7 divided by IB. You can find out IB. IB is nothing but IC divided by beta. ICQ is given 2 milliampere. So 2 milliampere divided by beta 80. That is going to give you the base current. Now substitute at the input side. 12 minus 0.7 divided by the value of IB, you will get the value of RB. Similarly, 12 minus 6, it is given that VCEQ is 6 volts. So 12 minus 6 divided by IC, 2 milliampere. That way you are going to get the value of RC. Later on, let us see whether base to collector junction is reverse biased. Quickly tell me the answer within the next 2 minutes. Okay, Sayan has given the answer. RB is 452 kilo ohms. Let us verify that later. What about other students? Other students also have to try out. Even if the answer is wrong, don't worry. But you will have to practice. You will have to work out at least. Without working out, you will not be able to understand the second year's electronics and communication courses. "47 students are in the class, whereas only one student is giving the answer. What about the others?" Okay, again Sayan has given the answer. RC is 3 kilo ohms. Let me tell the answer. RC is 3 kilo ohms. Correct. 12 minus 6 divided by 2 milliampere. RC is 3 kilo ohms. IB we get 2 milliampere divided by 80 is 25 microampere. So RB is 12 minus 0.7 divided by 25 microampere is 452 kilo ohms. Yes, Sayan, your answers are correct. No. Rohit is telling some other answer. No, that is not correct. Check your calculations. Now finally we have to find out the base to collector junction. Let us find out VBC. VBC is VB minus VC. VB is 0.7, VC is already 6 volts. So we already know the answer. Is 0.7 minus 6 is going to be negative. VBC is 0.7 minus 6. VCE is already given. VCE is nothing but VC because emitter is grounded. So 0.7 minus 6 is minus 5.3 volts, which means that the base to collector junction is reverse biased. Okay, let me go to the next exercise. Just look at this exercise. This is slightly a different exercise. Given that VCC equals 15 volts, IBQ equals 20 microampere and IC sat is 6 milliampere. Design a fixed bias circuit with beta equals 120 and determine the quiescent point of the circuit. Here ICQ and VCEQ are not given. Quiescent point you will have to determine. But quiescent point's base current is given and beta is given. So naturally you can find out ICQ, but IC sat is given. So if IC sat is given, what are you going to find out? You just think about it and you tell me the answer. Just understand this problem and find out whatever you can find out in your own way. Later on I will show my answer. Okay, RC is 2.5 kilo ohms. Okay. Yes, RC is 2.5 kilo ohms. How? IC sat is given as 6 milliampere. When IC sat is given as 6 milliampere, then naturally 15 volts divided by 6 milliampere is 2.5 kilo ohms. That is correct. Now what else can you find out? Now please remember ICQ is different from IC sat. ICQ is quiescent point or active region. IC sat is when the transistor is completely saturated. RB is 286 kilo ohms. Let me see. No. Check your calculations. RB is 15 and minus 0.7 divided by 20 microampere. See, the base current given is 20 microampere. So VCC minus 0.7 divided by 20 microampere. VCC minus VBE divided by IB. That is, answer is 715 kilo ohms. So we got this RB, we got this RC. That means the transistor's design is done. Sorry, transistor's biasing is done. Now we also have to find out ICQ and VCEQ. We have to find out the quiescent point. How do you find ICQ? ICQ is nothing but IBQ into beta. 20 microampere is given into beta is 120. So ICQ is 2.4 milliampere. Now when we know ICQ 2.4 milliampere, we can easily find out VCEQ. How? VCC minus ICRC. VCE is VCC 15 volts minus IC into RC. RC we have 2.5 kilo ohms. IC we know 2.4 milliampere. Please understand, we are not going to substitute IC sat here. we are going to substitute ICQ here. IC sat is given here so that we could find out RC value, the collector resistors value we could find out. Whereas the transistor is not in the saturation region, transistor is in the active region only. So when we have ICQ 2.4 milliampere, we have to substitute the quiescent current only. We should not substitute the saturation current here. That is where students get confused. So in any transistors biasing, we will never be using saturation current for the purpose of finding out the Q point. That saturation current can be used only for plotting the load line. So here VCEQ is 9 volts, which means supply voltage is 15 volts. Ideally, we were supposed to have VCE as 7.5 volts. And IC sat is 6 milliampere. Ideally, we should have had ICQ equals 3 milliampere. But slightly there is a deviation because of the values of the resistance, and that is again because of the specifications. So it does not matter. Still we can say that the transistor is in the active region only, but it is not in the exact middle region of the load line. Okay, these are the exercises which are based on base bias. In my next slide, I am going to give you some different type of exercise. Let us see this emitter bias or self bias. This we had already discussed in detail in the theory class. And you already know about this RB and RE and RC. One additional value of resistance is given so that we are preventing the transistor to go into saturation. We are ensuring that the transistor will remain in the active region only. Because if the transistor saturates, there will be a voltage drop across this RE, and that VE, the voltage across RE is denoted as VE. This VE is going to reverse bias this PN junction because the cathode is here connected to the plus side here. Across resistance there will be plus here and minus here. Let me annotate. There will be, if the voltage is induced across this RE, then we are going to measure this VE across RE with the plus at the top and minus at the bottom. Okay. Now this is VE. Now if there is a voltage drop across this RE, this PN junction's cathode is connected to the voltage which is positive. So naturally this transistor is prevented to go into saturation. It will remain in the active region only. That is how we are ensuring through this resistance. Please revise the theory class once again, which we had discussed in detail earlier. Now I am going to slightly deal with the mathematical analysis of this particular circuitry. At the input side, let us apply KVL. VCC is equivalent to IBRB minus VBE minus VE. VE is nothing but IERE. So VCC minus IBRB minus VBE minus IERE equals 0. When you apply KVL at the input side here. When you apply KVL at the input side here. So here it is VCC minus IBRB from this point till this point, from the supply till ground, we have this input loop. So total voltage is VCC, voltage drop across RB is IBRB, voltage drop across PN junction VBE, voltage drop across RE is IERE. So that way VCC minus IBRB minus VBE minus IERE equals 0. Now IE is nothing but 1 plus beta into IB. This expression you are already familiar with. IE is nothing but 1 plus beta into IB. We will substitute that. I will bring out the two terms IBRB and IERE to the right hand side. VCC minus VBE is equal to IBRB plus 1 plus beta into IB into RE. Now we can write an equation IB, because taking IB as common here at the right hand side, I will bring that IB into left hand side. IB equals VCC minus VBE divided by RB plus beta plus 1 into RE. In most of the time we will be ignoring this 1 because beta is always in the range of 60 or 80 or 100. Now adding 1 will not make any major difference there. So most of the cases we will be ignoring this beta plus 1. But anyhow, for accuracy, we are keeping this beta plus 1. Beta plus 1 and 1 plus beta are one and the same. So we have an expression for this emitter bias or self bias as IB equals VCC minus VBE divided by RB plus beta plus 1 into RE. Now using this, we can easily find out IE. Once we know IB at the output side, we can apply KVL once again, and we will have VCC minus ICRC minus VCE minus IERE equals 0. Approximating ICA and IE, we can write that VCE equals VCC minus IC into RC plus RE. This expression I had discussed earlier also. This is just a recapitulation today. So, given the circuitry, first you have to find out IB. This formula you will have to memorize. You have no choice. This formula you will have to memorize. Even the lower formula also you will have to memorize. Even if you understand also, it is better that you memorize. Sometimes even if you understand, you may not recall the equations. The equations, if you have to recall again and again, you will have to memorize this many number of times. You keep on telling this formula some 10 times, automatically it will remain in your memory. Keep on telling IB equals VCC minus VBE divided by RB plus 1 plus beta into RE. That is how I remember. Here it is given as beta plus 1. Beta plus 1 and 1 plus beta are one and the same. So IB equals VCC minus VBE divided by RB plus 1 plus beta into RE. VCE equals VCC minus IC into RC plus RE. These two equations you remember. Now based on this, I will give you the exercise in the next slide. This is the exercise for the self bias or emitter bias. Now quickly solve this. The question given is determine the Q point, determine IC sat and determine VBC. Quickly solve it. IB is VCC minus VBE divided by RB plus 1 plus beta into RE. That is the formula. Quickly substitute these values and tell me the value of IB. Then multiply it by beta and tell me the value of IC. Later on apply the formula VCE equals VCC minus IC into RC plus RE. You will get the value of VCE. So determine the Q point. Later on I will tell you how to find out IC sat. Okay, Sayan has given the answer as 44.8 microamperes. Other students are not trying. I don't know why. Students have to work out these exercises. You will have to remember the formulae. Otherwise, later on, we will be finishing module 1, we will be going on to module 2, then module 3, module 4, module 5. This semester will go on like a marathon where you will have 6 courses. Each teacher will keep on completing the modules. So it will become heavy for you if you don't start working out the exercises. Don't take the second year lightly. Second year electronics and communication is tougher. Don't think that just like first year, even in second year it will be so easy. First year is basically a revision of science, whereas In second year, you are going to get into the core of engineering. So follow all these classes, work out all these exercises, only then it will be easy for you. Otherwise, you will get overloaded in future. Okay. So Sayan and Harshit Gowda and Rohit are giving the answers. Let me tell the answer now. IB is 20 minus 0.7 divided by 430K plus 51 into 1K. VCC minus VBE divided by RB plus 1 plus beta is 51 because beta is 50. 1 plus beta into RE. So the answer is 40.12 microamperes. Who all have got it? Yes, Cyan has got it as 44.8 microampere. Slight difference is there. Maybe your calculator model is slightly different from my calculator model. Anyway, fine. Now, you forgot beta. Okay, fine. Now, IV is this value. ICQ is, beta is 50. 50 into 40.12 microampere equals 2.01 milliampere. Okay, that is correct. ICQ, it should be accurately 2.01 milliampere. Rohit has got 2.23 milliampere. And Sayan has got 2.2 milliampere. There is a slight difference. Anyway, now what is VCE? VCEQ is VCC minus IC into RC plus RE. I'm sorry, in this PPT I have put into symbol. I should put plus symbol there. I think something is wrong here. Even I don't know. I worked this out. Maybe whether I did an error or is it correct, I don't know. I'll have to verify this. So VCE is VCC minus IC into RC plus RE. So 20 minus 2.01 into 3. This is correct. Answer is correct. I should put a plus symbol here. Instead, I have put a into symbol in a hurry of slide preparation. Anyway, I will correct it today. So 2.01 plus 3 is 5.01. 20 minus 5.01, you will get 13.97 volts. IC sat is, how do you find out IC sat here? Somebody gave the answer of IC sat. Who? Harshit Gowda has given the answer 10 milliampere. No, that is not the correct answer. See, in the earlier case, in the base bias case, emitter was connected to ground. So what we used to do was, we used to think that transistor is completely switched on and we used to take this VC as 0 volts. We directly used to find out VCC divided by RC. But in this particular case, there is RE. We cannot ignore this RE. So here, if we have to calculate IC sat, we should assume that transistor is completely switched on. If the transistor is completely switched on, between collector and emitter, it is 0 volts. When the switch is completely on, across the switch, there is no voltage ideally. This is what I have been telling you earlier also. So across the collector and emitter, it is 0 volts. But as current is flowing through the output path, you will have voltage drop across RE as well. So IC sat is 20 divided by 3K. Because it is 2 plus 1, totally 3 kilo ohms is there between VCC and ground. So 20 divided by 3K is 6.67 milliampere. So whatever method you followed for the base bias is not applicable here. You would have done what? 20 divided by 2 kilo ohms you would have done. No, that is wrong. It is 20 divided by 3 kilo ohms because from supply to ground, totally 3 kilo ohms is there, assuming the transistor in saturation. So that is IC sat. Now let us find out VBC. If my answer 13.97 volts is correct, then my VBC also will be correct. Otherwise, I'll have to verify the answer later on. Anyhow, ICQ is, okay, how is it 20 divided by 3K? Because RC is 2K. I told you no, RC is 2K, but there is this RE as well. Okay, let me annotate this. Now, at the output side, right from VCC till ground, you come this way. Okay, when you come this way, from the supply voltage 20 volts, current is coming into 2K and then current is going into transistor, then current is coming into 1K as well. Then it is going to ground, right? So how can you ignore this 1 kilo ohms? In the base bias, this Re was not there, but in the emitter bias, this Re is there, which cannot be ignored. We are only assuming that the transistor is completely switched on. That means between collector and emitter, it is 0 volts. But otherwise, when current is flowing through this 1 kilo ohm resistance, there will be a voltage drop across this also. So you will have to consider all the resistors which are coming in this particular path. You cannot say only 2 kilo ohms. So in case of the self bias or emitter bias, the formula for this IC sat is VCC divided by RC plus RE. That is how you have to analyze it. Now let me go further. We have to find out VE. VE is 2.01 into 1K. 2.01 milliampere is the current. We assume that IC equals IE. So into that 1K, that milli and kilo I have not put. So VE is 2.01 volts. Now VE is 2.01 volts. VC, see, at the collector it is 30.97 volts. At the emitter it is 2.01 volts. So totally collector voltage with respect to ground is 13.97 plus 2.01, that is 15.98 volts. I don't know why students are keeping on waiting in the lobby. Anyway, VC is VCE plus VE. Just visualize this output side. We want to find out the voltage at the collector. Voltage at the collector is voltage between collector and emitter and the voltage at the emitter. In this particular circuitry, emitter is not connected to ground. So VC is VCE plus VE. That is 13.97 plus 2.01 equals 15.98 volts. So now VB is 0.7 plus 2.01. The voltage at the base, earlier it was only 0.7 volts. Now in this particular example, it is not 0.7 because there is this VE. So VB is VBE plus VE. VBE is 0.7 plus VE 2.01. So VB is 2.71 volts. Now VBC is VB minus VC. Voltage at the base minus voltage at the collector. That is 2.71 minus 15.98. That is coming to minus 13.27 volts. Now this means that the transistor is in the active region. The power supply is 20 volts, whereas the Q point is at approximately 14 volts. IC sat is around 6.67 milliampere, whereas ICQ is around 2.01 milliampere, which means that the transistor is in the active region only, but it is not in the exact middle of the load line. If it has to be exactly middle of the load line, then we should have VCEQ equals 10 volts, and we should have ICQ equals IC sat by 2. That is 6.6 divided by 2. We should have got 3.3 milliampere. That is not the case. Anyhow, this VBC is negative, which means that base to emitter junction is forward biased and base to collector junction is reverse biased. Let me stop with this for today. It is already time now. I will see you in the next class. I will be posting the attendance link in the Google class.